The final thing we're going to talk about with resonance is the relative importance of resonance structures. So we're going back from the hybrid to looking at individual structures. But what we want to think about is how much does each resonance structure contribute to the hybrid? Or put another way, how much does each structure look like the hybrid? The major resonance contributor looks the most like the resonance hybrid. There's a few guiding rules that we're going to use for this. The first has to do with identical structures. If you have identical resonance structures, they're going to be equally important. So we saw that with like the allylic carbocation and allylic carbanion. So here, I'm going to show you something we're going to start doing a little bit as we get more and more comfortable. We may not always draw in the lone pairs because we automatically know there's a lone pair on this carbon. So we can show the other resonance structure like this. These two structures are equivalent. We have the negative charge on the carbon next to the pi bond. They're equally important. They contribute equally to the resonance hybrid. The second thing has to do with charges, and the more important structure has charges minimized. So going back to our ketone example, we have two resonance structures. Like this. But in the case of these two, the one on the left has minimized charges. It's uncharged. So it is the most important or the major resonance contributor. The third thing is that resonance structures with complete octets are more important. So let's look at this, and I'm drawing in the hydrogens just so we can keep track of things a little more easily. Okay, here we have a lone pair next to a positive charge. We know we can draw a resonance structure where that lone pair comes down to form a pi bond. And we end up with the positive charge on the oxygen. Now, if you look at these two structures, this carbon on the left here lacks an octet. It only has 6 electrons. The oxygen has 8 electrons, so it's good. The hydrogen has its duet, so it's good. Well, in the other resonance structure, now because we've shared oxygen's lone pair, this carbon now has 8 electrons. It has an octet. The oxygen, even though it has a charge, it still has its 8 electrons and it has its octet. So this structure on the right has all atoms have an octet. So it's the major contributor. Meaning the resonance hybrid looks most like it, or looks more like it than it does this structure. And the fourth rule, structures that place a negative charge on the more electronegative atom or a positive charge on the more electropositive atom are more important. So here's an example of that. Here we have a negative charge on the carbon, which means there's a lone pair there. Through resonance, I can move that here to form a pi bond and move this pi bond up onto the oxygen. That oxygen has 2 lone pairs. We draw the resonance structure. Now that oxygen has 3 lone pairs and the negative charge. We have a double bond here. In this case, The resonance structure on the right is more important, or the major contributor. Because we have the negative charge on the more electronegative oxygen. So now if your mind's going back to our previous rule, rule number 3, and something might not be making much sense because we had this. And we said that the one on the right is more important. But the one on the left has the positive charge on the more electropositive atom, because oxygen's more electronegative than carbon. So the answer is you want to apply these rules in order. So rule 3 supersedes rule 4. Having an atom, or having all atoms with octets, is more important than putting the positive charge on the more electropositive atom.